This question has a slightly different wording than the ones that we've looked at in the past. In the ones in the past, we were expected to set up an integral. In this one, they're giving you an integral and they're saying, interpret this as the area of a region. Okay, well, what is that supposed to mean? Well, we know that if I've got two curves, one minus the other, I can think of that as the area of the one curve minus the other. But the weird thing here is that we've got these absolute values. So what are absolute values, really? Of course, you're looking at the distance of zero, but if I've got the absolute value of a function, basically, it's the value of the function where the value of the function is positive and negative f of x where f of x is negative, right? That's just the meaning of the absolute value. So to figure out what this really means, I have to find out where the function, my function sine x minus cosine 2x, is positive or negative. So that means I want to do a sign chart on the interval that I'm interested in, which is from 0 to pi over 2. And then I'm going to break it up into the positive and negative parts, have two different integrals, and make sure my signs are correct. Okay. However, notice they said interpret this as an area of a region. Maybe I can make my life a little bit easier if I think more geometrically, right? So let's try to draw the region, and I think the original wording says to draw the region as well, so we're not making ourselves extra work, but let's try to think of this as the difference between two functions. So let's draw y equals sine x and y equals cosine 2x and see what the heck that really looks like. Again, I want it from 0 to pi over 2. Well, I probably need something here, right? I'll put pi over 4, negative 1, and 1. So sine x, it's 0 at 0. It's 1 at pi over 2. And just goes up my nice little sine curve. So maybe that's not the prettiest, but you get the idea. Now, what about cosine of 2x? Cosine, it's 1 when x equals 0, but this isn't cosine of x, it's cosine of 2x. So it has a period as half, right? And if I just kind of mentally think about that, so it would expect that instead of going at pi over 2, instead of being 0, it's going to be negative 1. How do I know that? Well, if I just mentally put that in, pi over 2, cosine of 2 times pi over 2, it's cosine of pi. That's negative 1. Okay, so we know that that's there. And then, of course, at pi over 4, it's going to be cosine of pi over 2, which is 0. So that looks like that. Again, the 2 squashes the period. So my cosine look like that. So this is the region that we're interested in, right? Let me let me fill this in a little bit. And so we see similar to some of the other problems that we saw, we have two different parts of the integral, and we can break this up into two pieces. So let's look at this. So this one is y equals sine x. And this one is y equals cosine of 2x. All right. So now I'm claiming that the integral that they want with the absolute value is going to be the same as this yellow region. Why am I saying that? Okay. Why? Because the absolute value is basically taking care of the sign business. So on this first part, on part number 1, cosine is bigger, the cosine curve is bigger than the sine curve, right? So this would actually, the value would be negative. So I really would have cosine 2x minus sine x when I put the absolute values. On the second part, the opposite is true. Sine x is bigger. So that's going to be the positive part. So if I simply write down the area of the yellow, I need to find out that point, but I'll do that in a minute. But let's set it up first. On So let's do it with the one and the two. That way it looks good. On one, the cosine part is bigger, so it's cosine 2x minus sine x, right? And then on 2, the sine is bigger, so it's sine x minus cosine 2x. And you can absolutely see, just geometrically looking at that, if I were to find the sign chart for this function, sine x minus cosine 2x, it's exactly going to work that out that way, right? The function is 0 here at the point where they intersect, and the sine x is first, so this part number 1 would be a negative, and this part on number 2 it would be a positive. Okay. So I do need to find out where they intersect. I still have to do that work. Okay, I just don't have to, because I drew it, I don't have to check what's positive and what's negative because I can see it from the graph. But we still have that last piece of work. What is the point of intersection? That doesn't take me a little bit. So I'm going to put it here. So point of intersection. So what we're trying to do is find where sine x equals cosine 2x. Now I'll tell you that in my class, I absolutely do expect you to be able to do a problem like this on a homework assignment because you can look up stuff. On a time test or a quiz, probably not going to be asking you to know what you have to do here because what you have to do is you have to use trig identities. And the trig identity you need is that cosine of 2x is cosine squared x minus sine squared x. And if you had to know that, I would probably give it to you, but I wouldn't really want you to take your test time working out extensive trig problems because now I still don't know how to solve for x. I need to get it all in terms of sine or cosine. I've got the sine there, so I might as well change cosine to sine. Remember, using my Pythagorean identity, which you are expected to know and use all the time, but that's like one of the biggies. So this tells me that I can put in 1 minus sine squared x there. This will give me that. So now my equation has become this, or 2 sine squared x plus sine x minus 1 equals 0, right? Which you should immediately recognize as a quadratic equation, right? Because you got sine squared and sine. So it's a quadratic equation in sine. So in other words, and we talked about this in one of the other problems, if I do z equals sine x, this becomes 2z squared plus z minus 1, which you can easily go ahead and factor here. So one of them is going to be 2 sine x. Let me leave enough space. That I didn't even change it. Darn. And then the other one is going to be sine x. And you have negative 1 plus 1 minus 1. You want a plus here, so it's going to be plus 1 and minus 1. All right, there we go. So this gives me two possibilities. Sine x equals 1/2 and sine x equals negative 1. All right, I only care about what's going on between 0 and pi over 2 because that's where my problem is. So sine x equals negative 1. I don't care about that because that would give me x over 3 pi over 2 plus whatever. So these not on my domain. This sine x equals 1/2. Who's that? Sine is the y x coordinate. No, sine is the y coordinate. See, I have to be careful. Sine is the y coordinate. It's the smaller than the x coordinate. So this is what we want. We want the root 3 over 2, 1/2 for my x there is pi over 6. That's the angle. Okay, so pi over 6 is the angle, pi over 6 is the point, pi over 6 is where we are here, which of course is nice because that's right, because it's less than pi over 4, so that makes sense. Okay, double check. I didn't screw myself up because if I had pi over 3 there, I would know I made an error. All right, so that's the point I want. So let's do this integral now. So this is what we're going to do. We're going to do this integral. And now we know that if I come down here, I'm going to put it over here. If it does, but do it, do it, do it. Woo! Did it. Now we know what our limits of integration are. The middle point is pi over 6. So we have this. And then it goes from pi over 6. I'll just live with it, right? Pi over 6 to pi over 2. Okay. Now, the rest is easy. That was probably the hard part because these are just straightforward. So cosine, derivative of sine is cosine. So this would be sine 2x and a 1/2 minus, okay, the derivative of cosine is negative sine. So I have to be careful there, right? Got that. And then sine x, the derivative of cosine is negative sine. So I have negative there. And then the derivative of sine is cosine, so it stays negative. Be careful with my negatives, right? Okay. And this is pi over 6 to pi over 2. And so all I have to do is shove this stuff in, see what I have. So I have 1/2 sine pi over 3 plus cosine of pi over 6 minus 1/2 sine 0 plus cosine of 0. And then the next one, double check. Okay, yeah, that was right. I'm just double checking my signs because they all screwed up. So, minus cosine pi over 2 minus 1/2 sine pi, and then minus all that, so it's going to be plus cosine pi over 6 plus 1/2 sine pi over 3. All right. That's good. Now, so sine of pi over 3, so that's this guy. This is pi over 3. This is pi over 6, right? So pi over 3, the sine is going to be root 3 over 2. It's going to be the longer. So I have 1/2 times root 3 over 2. Cosine of pi over 6 is also going to be the longer, root 3 over 2. Sine of 0 is 0, but cosine of 0 is 1. So we have to make sure that we keep that and it becomes a minus because of this minus there. Then I have cosine of pi over 2, which is 0, sine of pi, which is 0, and then, so let me just write those. This is 0, this is 1, be careful, this is 0, this is 0. Okay, so that one, remember. Cosine of pi over 6, we just said root 3 over 2. And then 1/2 of sine pi over 3, another root 3 over 2. So it looks like I have 3 root 3 minus 1. Oh, wait. No, 3 root 3 over 2. Like what? All right, that's better. Okay. And that's our answer. So we have our answer for our area. Our integral, and we interpreted it in terms of area using this picture. Now, if we didn't interpret it in terms of area, we could still do this. We would probably be more or less the same, work because we will have to find out where this function f of x is sine x minus cosine x is 0, where it's negative and where it's positive, and then we would set up our integral as the two different integrals on those different regions. So it's probably about the same, but maybe I think kind of seeing it as the picture makes it a little bit clearer.